Capacitor is a device to store electrical energy or electrical charge, right? Since this is the energy of interaction, both plates interact with each other, right? Since this is the energy of interaction, this is the electrical potential energy of a capacitor. Now, how do you find this potential energy and how it is stored in a capacitor? This energy is stored in the electric field between these capacitors. Energy density U of the electric field is given by 1 over 2 epsilon 0 multiplied E square, electric field square. And we know that the electric field strength inside the capacitor, it's uniform. Now, if you want to find the potential energy, we just need to integrate energy density over the volume between its plates, right? So potential energy is given by U dV. Now, if we integrate it, we get 1 over 2 epsilon 0 E square multiplied the volume between its capacitors. So it is just V, right? V can be written as S, the surface area of one plate, multiplied the distance between the plates. I can also write it in a bit different form. For example, 1 over 2 multiplied epsilon 0 S divided by D multiplied E D square. So epsilon 0 S divided by D gives you the capacitance of that capacitor, and E multiplied D is just the voltage across its plates. So it's just big U square, right? So this is small u. This is called the energy density, and the big U is just the voltage between its plates. Then finally, we can find that the potential energy of a capacitor is just 1 over 2 C U square. We can also write it in a bit different form if you use Q over C instead of voltage. We can find that it is also 1 over 2 Q square divided by C. In this derivation, we use the fact that the electric field strength inside a parallel plate capacitor is uniform, right? It's constant. So integration was very simple and got electrical potential energy of a parallel plate capacitor. But the final expression for potential energy, this is valid for all types of capacitors. Okay, now you can use that formula for spherical capacitor, for cylindrical capacitor, and so on. And why it is valid for every capacitor? Because now let's derive it in a bit different way. For example, consider initially our capacitor plates is uncharged, right? There are 0 charges on each plate. Then when capacitor is being charged, the charge builds up on each plate, right? Then the work to move dq charge from negative plate to positive plate is given by the following formula, which is just dA equals U multiplied dq, where U is the voltage between these capacitors when the charge is Q. Okay, so it's just Q divided by C dq. Now, if you want to find the total work to charge this capacitor to a charge Q, then we need to just integrate it. So A equals integral dA, which is just charge goes from 0. So initially the charge was 0, right? Goes to the maximum charge, which is BQ, and inside, under the integration, there is 1 over C Q dQ. The integration of Q gives you Q squared divided by 2, right? So it is Q squared divided by 2C. Now integration goes from Q 0 to BQ. Then it is just Q squared divided by 2C. This is the work which is done by the external forces on a capacitor. So we give some energy to capacitor, and this energy is spent to increase capacitor's potential energy, right? Then initially, if we assume that the potential energy of a capacitor is 0, since there is no any charge on the place, they are not interacting. The interaction energy is 0 at that point. Then the potential energy is just the work which is done by the external forces to charge a capacitor to a charge Q, and it's just BQ squared divided by 2C, or CU squared divided by